Hello guys, welcome to homework number 23. I'm going to share the slides now for the solutions to this homework. So the first problem is focus on concept question 2. What is the RMS, the root mean square current, IRMS, and the circuit when VRMS, the root mean squared voltage is 30 volts, the capacitance is 2.5 microfarads, and the frequency is 4 kilohertz. So it's just a capacitive circuit, the capacitance, and then so XC is the reactive capacitance, which is like the resistance offered by the capacitance in the circuit. It's 1 over 2 pi FC, so we can calculate that. 2 pi frequency is 4 kilohertz, which is 4,000 here. Then the C, the capacitance, is 2.5 microfarads, which is 2.7 microfarads, which is 2.7 times 10 to the power negative 6. So I compute that my capacitive reactance in ohms. Then my IRMS, which is asked, is VRMS over XC. So 30 divided by this answer, that just gives us the answer there for that. Go to the next problem. It's the same RMS current. We are given VRMS, but now it's an inductive circuit. So I have L, then inductance. So the capacitive inductance here. Sorry, the inductive reactance. Inductive reactance. Capacitive inductance. XL is 2 pi FL. For the capacitance, it's 1 over 2 pi FC. But for the inductance, is 2 pi FL, 2 pi times the frequency, 1.5 kilohertz, 1500 hertz times 1.7 millihenries, 0.0017 henries, and then we get that. Still in ohms, so we just use like our Ohm's law to get the current voltage over the inductive reactance. So 45 over that, and that gives us the answer in amperes for the current. So we just keep going. These are simple problems. We have to find the maximum voltage supplied by the generator in the AC circuit. Can be represented by this drawing. So the instantaneous voltage at this time. So in this diagram, this Phasor diagram we have here, the instantaneous voltage is just the Y component at this point. So it is the Phasor component along the vertical axis. This is just voltage and current. Okay. So here we have 4 Phasor diagrams to present, each of these represent a different circuit. V0 and I0 represent respectively the maximum voltage and the maximum current in the circuit. Which one is only a resistor? So for an inductor, we know that current lags behind voltage. Then for a capacitor, current is ahead of voltage. So for a resistor, current and voltage are in phase. So D is the one that should be for a resistor. They are in phase, they are together on the same. We have no angle between them. Okay. Then focus on concept question 09. The same AC voltage is applied across a resistor and a capacitor, and the same RMS current exists in each. Do both dissipate the same average power? No. So it's only the resistance that takes power, that power is dissipated to the resistor in an RC circuit, not the capacitor. So the average power will be dissipated only by the resistor. Then focus on concept question 03. Suppose the frequency F of the current in an AC circuit goes to 0, which means that the current becomes a direct current. Which circuit element will not permit charge to flow in the circuit? So a capacitor will not permit charge to flow because it has the largest reactance. When F goes to 0, here 1 over 0 becomes infinity, very big. So the reactance becomes large. So it will not allow charge to flow in the circuit. And that is why a capacitance, it just acts like as if you are charging it at that time. It just sucks all that. Okay, focus on concept question 04. What happens to the capacitive reactance and the inductive reactance if the frequency of an AC voltage is doubled? So capacitive reactance XL is 2 pi FL. When you double the frequency, you just double the capacitive, the inductive reactance. And the capacitive reactance is 1 over 2 pi FC. So when you double the frequency, you have half of what you're supposed to get for the capacitive. So the XC decreases by a factor of 2 and XL increases by a factor of 2. Just from these two formulas, this is inductive reactance and this is capacitive reactance. Focus on concept question 10. The AC generator in a series RLC circuit has an RMS voltage of that. The values of resistance, capacitive reactance, and inductive reactance are already given. So XC and XL are given. So note, this is not C and L, XC and XL. So this 1 over 2 pi FC already computed, 2 pi FL already computed. So sometimes you might be given C and L, so you have to compute 2 pi FL and 1 over 2 pi FC yourself. But now I'm giving XC and XL, so when I have a resistor, or a capacitor, an inductor, and a circuit, the total resistance offered is called the impedance. That impedance Z, VRMS is RMS times Z, is computed if they're in series as R squared plus XL minus XC all squared. So I put this here, my IRMS becomes VRMS over Z, which is VRMS over R squared 30 squared plus 90 minus 50 squared. So this is 30 squared plus 40 squared. That is 2500 under here. Square root of 2500 is 50. 120 divided by 50 will give us 2.4 amperes for the current. Right? Next, it says here, the values of the resistance and inductive reactance in a series RLC circuit are respectively R, XL. So what must be the value of the capacitive reactance such that the current is maximum? So when you want the current to be maximum, then you want to operate in the resonant frequency. And when you operate in resonant frequency, from here you can even tell, for you to get a maximum current, you want the denominator to be small. For this denominator to be small, XL and XC has to be equal. You have just R. So XL equals XC, so that XL minus XC goes to 0. You have only V over R. That's when you can get the maximum current. So for maximum current, XL equals XC, which is 50 ohms. So if you equate XL equals XC, 2 pi FL equals 1 over 2 pi FC, you calculate your F there, you get what you call the resonant frequency. We're going to get that formula and use it for some other problems. Okay. Focus on concept question 14 says, when the AC generator in the drawing operates at a high frequency, is the current in the circuit greater than, less than, or the same as when the generator operates at low frequency? Okay, so we're going to use these formulas. So the current is greater at higher generator frequency because the capacitor has very small reactance. So when the frequency is high, you see here, it's okay, it's just a capacitive and a resistor circuit. This is when the frequency is high, you're going to get small reactance. So when your reactance is small, you're going to get high current. Is that okay? Okay. So it has a very small reactance and behaves as if it were replaced by a wire with no resistance. Therefore, the circuit behaves as two resistors, R1 and R2, connected in parallel. So this will offer, no reactance at all when the frequency is very high. A capacitor and inductor are connected to an AC generator in two ways, in series and in parallel. At low frequencies, which circuit has the greater current? So just at this, okay, when you connect in series and you connect in parallel, you can tell from parallel connection, you always get a smaller, just assume these are two resistors, for instance. In series, you add, in parallel, you take the inverse, remember? So the parallel one will give a smaller impedance. So because the impedance is smaller for the parallel circuit, so we say the parallel circuit will have the greater current compared to the series circuit. So when resistance is small, your current is large. When resistance is large, your current is small. Okay. Next problem, focus on concept question 16. If resistance R in an RLC series circuit is doubled, by what factor does the resonant frequency change? So the resonant frequency does not change because the resonant frequency doesn't depend on resistance. So remember, when you equate 2 pi FL equals 1 over 2 pi FC, you're going to get the resonant frequency from that calculation. Solve for F, you get F squared. When you solve for F, you're going to get F as 1 over 2 pi square root of LC. It doesn't depend on R. So this is the resonant frequency, is independent of R. Chapter 23, problem 19 says a circuit consists of a 207 ohm resistor and a 0.204 Henry inductor. These two elements are connected in series across a generator that has a frequency of 129 Hertz and a voltage of 270 volts. What is the current in the circuit? And determine the phase angle between the current and the voltage of the generator. And note that the AC current and voltage are RMS values and power is an average value unless indicated otherwise. So we're just going to take everything we have, the inductor, the capacitor, and the RMS voltage and frequency. So we see XL is 2 pi FL, the frequency, and the Henrys are used to create XL. Then Z is R XL minus XC, but we don't have XC here. So it's just R squared plus XL squared, okay? It's just an inductor and a resistor circuit, no capacitor. So we'll do that, we get this as our impedance. So current is V over Z. So we just get that here. The V is given in the problem. Then the phase angle is the new thing here, is just XL minus XC over resistor. So inductance minus capacitive, inductive reactance minus capacitive reactance over resistance will give us tangent of the angle, the phase angle. So, but there's no capacitive inductance, so it's just inductive. There's no capacitive reactance, it's just the inductive reactance. So we have XL over R. So we get our phi angle to be tan inverse of that. Okay. Chapter 23, problem 22 says a 20 ohm resistor and a 1.3 microfarad capacitor are connected in series across the generator, determine the power delivered. So we're going to get XC first because we need that. It's 1 over 2 pi FC. And average power delivered in an RLC circuit, RC circuit is V squared R over R squared plus XC squared. So we just put this here and we get the answer 110 watts for the average power. So this one says a series RLC circuit, that's chapter 23, problem 31, has a resonant frequency of 490 kilohertz. That's 490,000 hertz. If the value of the capacitance is that, what is the value of the inductance? So we're going to use this. We have the resonant frequency, we have the capacitance, we're looking for L. So solve for L here, you get this. And you just put in the L and the C and F naught, and you get your Henrys for L. And the last problem is chapter 23, problem 33. So we're given the resistor, capacitor, and inductor, and the voltage resistor. So they are asked to find at what frequency is the current maximum, resonant frequency, 1 over 2 pi root of LC. And then what is the maximum value of the RMS current? So VRMS over Z. So at resonant frequency, at that, if you're saying the maximum value of the RMS current, at resonant frequency, XL equals XC. So our Z is just R, if you remember. So it's just V over R to get that maximum RMS current here. So you don't need to calculate the impedance because impedance has XL minus XC all squared, XL equals XC, that goes away. You only have R squared square root, which is just R. So, okay, thank you guys, and I will see you guys next week. Have a good one.